All right, so this lesson is about solving absolute value inequalities. So remember when we talked about absolute value equations, first of all, absolute value is a measure of distance, so we talked about how that was always positive. When we talked about solving equations, remember we had the whole idea of we need visitors to leave the jail before somebody can go on parole, and then once somebody does go on parole, they can choose to be good or bad. So kind of hold on to that in the back of your mind for a minute. And before we actually start solving, we're going to start with word problems because I think that's going to help you make sense of why we solve them the way that we do. Okay, so some things that I want you to write down in your notes. First of all, write this kind of top bullet point here. The absolute value inequalities are often used to model real-world situations involving margins of error or tolerance. So if you've never heard these words before, that just means like if you're making something, industry has this a lot, like if you're making sheets of aluminum, for example, like for cans. That's what the Arconic Alcoa plant does here in town. They have to be a certain thickness, and if they're too thick, they're going to throw out those cans, and if they're too thin, they're going to throw out those cans because they don't meet the specifications. So that's the type of error or tolerance we're talking about. And then you can pause this video. I want you to read example 3, and if you want to be lazy and you don't want to write all that down, you can just write these bullet points down for the problem itself so we have them in your notes. All right, so this problem is talking about boards that are being cut, and I'll go ahead and fill this in. Our boards are being cut to, the goal is for them to be 3.25 meters long. So if you think about that on a number line, I would like for all the boards to be exactly 3.25, but that's not going to happen every single time, and I don't want to waste everything that's not exactly that. So it says that the lengths can differ by at most 0.02 of a meter. So that's how far off that could be. Now that could be that they're 0.02 of a meter larger or 0.02 of a meter smaller. All right, so that's going to leave me at 3.27 or at 3.23. So if we think about the solution here, I could have a board that is 3.25, or I could have a board that's 3.27, that's also acceptable, or 3.23, or really anything in between there. So it's not like it has to be exactly 0.02 meters off, right? It doesn't have to be that off. It just has to be that or less. So then our solution set now is not just specific points, but it's this whole range of points right here. And then if we think about modeling that in an inequality, we want to say then that the error, how far we're off by, is less than what they're giving us. So we calculate error by subtracting the actual amount from the goal amount. So that's the actual amount L minus 3.25. Right, that would tell us how far off any given piece is. And the goal is that the error is less than or equal to 0.02 because we don't want to be off by any more than that. So thinking about this, I want you to notice that error, or less than or equal to, gives you something that looks like that. If we were looking at a word problem, so let's look at one more. Let's say this time we're looking at a word problem of something that's unacceptable, that's outside that range of acceptable error. So here we're still going to say the same thing. We're calculating error the same way, and that is to say our goal value minus what we actually have, and I actually wrote that backwards. I mean, I said that backwards. This is the actual value minus the goal value, if you want to label those. If we're thinking about what's unacceptable, that's going to be when that error there is greater than or equal to the amount of error we're supposed to have. So if it's greater than or equal to, that's going to be greater than or equal to 0.1. And if you think about that on a number line, this time we're talking about the error that is unacceptable. So we're going to be talking about 3.9 and greater, or 13.9 or 13.7 and less, right? This greater than or equal to is going to give us a split because we're talking about the unacceptable values. We're not looking at this ideal range, we're looking at everything that's outside of the ideal range. Okay, so now that we know what some real-world examples look like on a number line, let's look at just some algebraic examples and kind of try to apply that. So we have two rules for absolute value inequalities. The first are if the absolute value is greater than a number where the number is positive. So we say greater than, that's when our error lies outside of what we were wanting. What it does is we're going to split the absolute value apart. So notice that when we do that, we still get our two inequalities or equations like we used to. Notice that I still have like a negative value and a positive value. Notice that on the positive value, the inequality symbol stays the same direction, and on the negative value, the inequality symbol flips. That should remind you of when you solved inequalities in Algebra 1. Anytime we divided by a negative, remember the symbol flips. And the other thing I want you to know is this word or. So you should remember that or, just like what we just said, the greater than is going to create a graph where, and I'll try to draw this above, where we've got something going to the left and something going to the right, because we're talking about things that are outside of the ideal range. On the other side of that, we've got this second rule, and that is if we have less than or equal to. So that's the ideal range. And remember, when we had this ideal range, we were talking about values that were stuck between two certain values. So this gives us like an in-between section, and we call this and I'll show you what that looks like in an example. But remember, we notice that we still have this negative and this positive value. So let's look at an example kind of all the way through. All right, so before we can do anything on this first example, just like with solving absolute value equations, we have to get visitors to go away. So I'm going to subtract 15 from both sides. That's going to give me absolute value x, wrote that backwards. Absolute value 4 minus x is going to be greater than 6. Okay, so this greater than means my error is going to be outside, or I can think about this as or. Another trick, I don't remember if I've taught you this before in Algebra 1, but this is more is or is kind of one way to remember that. That's a greater than symbol, so that's going to mean or, which means I should have arrows going opposite directions. So now I'm going to set up my inequality. So same that we did before. We have the option to be good, so greater than 6. I'm literally just copying what it looks like. Or I can have negative 6, and because this is an inequality, we need to flip the symbol. All right, so the absolute value part stays the same, 4 minus x. I'm just going to solve that out, subtract 4 from both sides. That's going to give me negative x is greater than 2. And remember, put a little star if you need to in your notes, because I'm going to divide right here by a negative 1, my symbol is going to flip around. So that's going to give me with x is less than negative 2. All right, if I work this other one out, negative x is less than negative 10, divide by negative, so x is now greater than positive 10. And when I graph that, remember I said or, so the goal is that these should be going opposite directions if I've done everything correctly. So I've got negative 2 and less, so that's open and to the left. And then I have 10, greater than 10, which is open and to the right. So that is exactly what I thought it was going to be. Or is going to be outside of that ideal range, so we're going to go opposite directions. All right, make sure you have that written down. Let's look at one more example. All right, so same idea here. We need to make any visitors that we have go away first. So I'm going to add 10 to both sides. So that's absolute value x plus 4 less than or equal to 8. All right, and now this is less than, which should make me think I'm within that ideal error range. So less than, if you want to make a note to yourself, less than is and. So if we solve this out, still going to have my two cases, less than or equal to positive 8, or my bad case when we get out of jail, negative 8, and we've got to flip the symbol, so that's now going to be greater than or equal to negative 8. I'm going to copy the absolute value part down, x plus 4. All right, subtract 4 from both sides. X is less than or equal to 4. X is greater than or equal to negative 12. And so let's look at this on a number line. I've got negative 12 and 4. So we're talking about less than 4, so that's going to be greater than and to the left. And we're also going to be talking about greater than or equal to negative 12. That's greater and to the right. And since this is and, we want to talk about where these two things overlap, which we just said right from that word problem that we're looking for that ideal range. What's the ideal range in the middle there? And so our answer is going to be just this range between negative 4 and 12. All right, we just want to kind of keep it within that range and not go any greater than or any less than those two things. Because if you notice, that's where our two inequalities are going to overlap. All right, so that's all you need. all you need to know for today. We'll work on this tomorrow.